The world's worst nuclear accident wasn't primarily caused by human error, it was engineered into the reactor from the start. On April 26, 1986, the RBMK-1000 reactor at Chernobyl exploded during a safety test designed to make the plant safer, killing at least 31 people immediately and contaminating an area still uninhabitable today. The catastrophe exposed fatal design flaws that Soviet engineers had known about for years but deliberately concealed. Nobel laureate Hans Bethe later described the RBMK as fundamentally faulty, having a built-in instability. The RBMK reactor had the highest positive void coefficient of any commercial reactor ever built, originally measured at plus 4.5 Valibrieff. In practical terms, when cooling water turned to steam, the reactor sped up instead of slowing down. This created a deadly feedback loop. More power meant more steam, which meant less neutron absorption, which meant even more power. Western reactors use water as both coolant and moderator, so losing water naturally kills the reaction. The RBMK used graphite blocks to moderate neutrons separately, meaning the reaction could continue even as cooling failed. Below approximately 20% power, this positive void coefficient became dominant, making the reactor inherently unstable and prone to sudden power surges. This exact condition existed during the fatal test, when operators were running at just 200 Pole-Standard Mängdendoppler thermal, about 6% of rated capacity, instead of the planned 700 to 1000 turn MW. But the void coefficient wasn't even the most insidious flaw. The emergency shutdown system, called AZ-5, contained a design defect so counterintuitive it sounds like fiction. Pressing the emergency stop button briefly made the reactor go faster. RBMK control rods weren't simple neutron-absorbing boron sticks. Each 7-meter rod had a 4.5-meter graphite displacer attached below the boron section. When fully withdrawn, this graphite sat in the middle of the reactor core with columns of water at the top and bottom of each rod channel. When operators pressed AZ-5, the rods began descending at 0.4 meters per second, far too slowly. For the critical first few seconds, the graphite tips entered the lower core and displaced the water there. Since water absorbs neutrons while graphite reflects and moderates them, the rods initially added reactivity instead of removing it. Engineers called this the positive scram effect. The emergency shutdown button became, briefly, an emergency accelerator. This flaw was discovered at the Ignalina nuclear power plant in Lithuania in 1983, 3 years before Chernobyl. The information was never communicated to Chernobyl operators. They had no idea that pressing the very button designed to save them could trigger catastrophe. The test scheduled for April 25, 1986 was straightforward: determine whether a coasting turbine could power coolant pumps during the 60-75 second gap before backup diesels activated. This gap was a genuine safety concern. The test was supposed to happen during the day shift, with experienced personnel. Instead, the Kiev electrical grid controller demanded Reactor 4 keep producing power for an extra 9 hours, pushing the test to the unprepared night shift. The team that inherited this critical experiment included Leonid Toptanov, a 25-year-old senior reactor control engineer with just 4 months of independent experience. Deputy Chief Engineer Anatoly Dyatlov, supervising the test, was notorious for dismissing operator concerns. Shift Supervisor Alexander Akimov, at 33, was more cautious but ultimately deferred to Dyatlov's authority. Around 0028 on April 26, power unexpectedly crashed from 1/600 millidollars to just 30 millidollars, a near-complete shutdown. This created a poison called Xenon-135, a fission byproduct that absorbs neutrons so aggressively it can shut down a reactor for days. Standard procedure required waiting 20-plus hours for the xenon to decay. Dyatlov refused. When Akimov and Toptunov objected, Dyatlov reportedly threatened to hand their jobs to the previous shift's operator who had stayed on site. To counteract xenon poisoning and restart the dying reactor, operators withdrew nearly all control rods. The RBMK-1000 had 211 control rods. Regulations required keeping at least 15 equivalent rods of shutdown capacity in the core at all times. By 0122, post-accident analysis showed operators had left only 6-8 equivalent rods, half the minimum. One physicist later described the reactor at this point as all gas and no brakes. At 012304, the test began. Turbine stop valves closed. Coolant pumps began coasting on inertial power. For 36 seconds, parameters appeared normal. Then at 01.2340, someone pressed AZ-5. The IAEA was never able to determine who pressed it or exactly why, possibly just routine shutdown after the test completed. The graphite-tipped control rods began their descent. Within 3 seconds, power readings exceeded 530 min$ and kept climbing. The positive scram effect, combined with the dominant positive void coefficient at low power, triggered a runaway chain reaction. Some fuel rods fractured from the heat, blocking the rod channels. Control rods jammed at roughly the 4-meter mark, halfway inserted, unable to stop anything. At or 1.23 Poten 58, roughly 18 seconds after AZ-5 was pressed, the reactor reached prompt criticality and uncontrolled, self-sustaining power excursion. Final readings showed 33,000 MW thermal before instruments failed. Some simulations suggest actual power reached 100 times rated capacity over 300,000 mW in less than 3 seconds. The energy release equaled approximately 40 billion joules, or 10 tons of TNT. 2 explosions occurred about 2 to 3 seconds apart. The first was steam, superheated water flashing to vapor so violently that it lifted the 2,000-ton upper biological shield, called the Elena, completely off the reactor. The second explosion's cause remains debated. Likely hydrogen formed when superheated steam reacted with zirconium fuel cladding, though some researchers argue evidence points to a small-scale nuclear fizzle. The explosion ejected roughly 25% of the reactor's graphite and nuclear fuel directly into the atmosphere. The 1,700 tons of graphite in the core, superheated beyond 500 point, caught fire when exposed to oxygen, sending a plume of radioactive fallout across Europe. The fire burned for days. Helicopters eventually dropped 5,000 tons of sand, lead, and boron onto the reactor, though much of it never reached the core. Unlike every Western commercial reactor, the RBMK had no containment structure. A proper steel-reinforced concrete dome would have doubled construction costs. Soviet nuclear officials had certified the RBMK as inherently safe when operated within established parameters, concluding that containment was unnecessary. The explosion released 50 million curies of radiation, equivalent to 500 Hiroshima bombs. The RBMK's design flaws weren't accidents. They were known. Scientists at the Kurchatov Institute recognized fundamental problems before the first units were built, but construction orders had already been issued in 1966 by the time concerns reached the Central Committee. By 1980, the Reactors Design Institute, NIKIET, had completed a confidential study concluding that accidents were likely even during normal operation. No action was taken. In November 1975, Leningrad Unit 1, the very first RBMK, suffered a partial meltdown with very similar characteristics to Chernobyl. Approximately 1.5 million curies of radioactive material was released over 1 month. The ministry blamed poor construction rather than design instability. Recommendations for safety improvements were ignored. Operators at Chernobyl practically knew nothing about this incident. The RBMK's flaws were kept secret partly because the reactor evolved from Soviet plutonium production reactors for nuclear weapons. Information about the design was classified at the same level as weapons data. Discussing the reactor's instabilities was forbidden, even among the people operating it. The KGB classified operating danger information as top secret to prevent saboteurs from exploiting vulnerabilities. The result, operators never learned their reactor could explode. In the control room after the explosion, Shift Supervisor Alexander Akimov quietly told Toptunov, "Don't worry, we did everything right. Something strange has happened." Dyatlov insisted the core couldn't have exploded. RBMK reactor cores don't explode. When operator Yuvchenko reported seeing graphite on the ground, material that could only have come from inside the reactor, Dyatlov dismissed him as confused. Despite receiving lethal radiation doses, Akimov and Toptunov returned to the reactor building. For hours, they manually opened coolant valves in flooded, highly radioactive rooms, trying to save what they still believed was an intact reactor. Akimov died on May 11, 1986. Toptunov on May 14th. Both received estimated doses exceeding 1,300 rem, more than 3 times the lethal threshold. Dyatlov, who survived, later reflected, "If I had known then what I know now about what kind of monster this reactor was, I would never have gone to work at Chernobyl. And not only me, nobody would have worked there." The initial Soviet report to the IAEA in August 1986 placed responsibility squarely on operators for violating procedures. But the 1992 INSAG-7 report fundamentally reversed this conclusion. The reactor design was poor from the point of view of safety and unforgiving for the operators. Most importantly, the physical characteristics of the reactor made possible its unstable behavior. The graphite tips were removed from all remaining RBMK control rods. Insertion time was reduced from 18 seconds to 12 with a new fast-acting system capable of inserting 24 rods in under 2 seconds. The void coefficient was reduced from plus 4.5 vries to plus 0.7 vry. Every fix was an admission that the original design had been fundamentally dangerous. Valery Legasov, the Soviet chemist who led the investigation and presented findings to the world, grew increasingly haunted by the institutional failures he had witnessed. On the second anniversary of the disaster, he hanged himself. In recordings made before his death, he concluded, "The accident was the inevitable apotheosis of the economic system which had been developed in our country over many decades. Chernobyl was not an accident of incompetent operators or unpredictable physics. It was the predictable result of a reactor designed for dual-use weapons production, built without containment to save money, certified as safe despite known fatal flaws, operated by staff deliberately kept ignorant of its dangers, and governed by a system that treated nuclear secrets as more important than nuclear safety. The operators made mistakes that night, but the reactor was waiting to explode from the day it was switched on.